Prim's algorithm, and minimal spanning trees. Okay, so we're going to talk about minimal spanning trees, and because of the logic of English, we're going to start with the tree part, then the spanning part, then the minimal part. And so let's start with tree. Now you might be used to the idea that a tree looks kind of like this, some nice curly branches there. That's not what we're talking about today, because mathematicians think they look a bit different. So for a tree, we must have no cycles, and a cycle means you've got like a dot, and all that, and then you connect it up, and you've made here a face. So they're not allowed. So no faces created by cycles, no loops. So a loop is when you have a vertex and it just goes around to itself, and you can have no multiple edges. So that means like you got a vertex and a vertex, and they're connected by two lines. So all of those things, no, not allowed. So if we got a bunch of vertices, 1, 2, 3, 4, 5, 6, like this, okay. So a tree connects things up. So we could say that's connected to there, and there, and there. There you go. That's a tree. Now, even that's a tree. You got like an isolated vertex. That little bit on the side is just like a tree, like a subgraph tree sort of thing. And it can be done in any way you like. It doesn't have to start in any particular way. You could do that. This is a tree. There are no cycles. If I did that, no, that's a cycle. So that is also a tree, and we can do all kinds of things. This is a tree. It's meeting all our criteria for a tree. So there's lots of ways to do a tree. Now, let's have a look at the idea of spanning. So spanning means, so this is the spanning part. So we had another rule here. Number 4 is must connect all vertices. Okay, so if I go like this, like this, like this, like this, like this, that's a minimal, not a minimal, a spanning tree. We haven't done minimal yet. So there's a spanning tree. It's connected all of them. If I erase that, I've got a tree, but not a spanning tree. All right, now the last part is the minimal part, and the best way to describe that is that if you've got to have weights on these things, so you might actually have a big graph like this, where they're all sort of connected up like this, and it says 3 and 4 and 2, 1, 0. You can have 0 on a weight. Don't know, sometimes for dummies, you'll have fun with dummies later. 5 and 3 and 2, and then you've got to try and work out how to connect them all for the lowest value. So when we say minimal, we're saying lowest value. And that's what we use Prim's algorithm for. So the best way to look at Prim's algorithm is actually to do an example question. Now I just highlighted these steps here, and I'm going to squish them off to the side when I do the question so we can look at all that means. But there's a nice little summary of the steps and the tips. Now this question for a past exam is just actually not even asking about anything. It's just saying we need a tree. There is actually a rule about this. So if you look at this, how many vertices have we got? We got 1, 2, 3, 4, 5. So it's actually just vertices minus 1 equals tree edges. So technically they should have said spanning tree, because that's a bad wording there. But if you've got 5 vertices, you can go 1, 2, 3, 4. Can you see we got 4? So the answer is B. And there's plenty of other ways of doing that. You can think about it as it's just like a cycle, and you can't close up the last one. So there's another way of showing the same thing. You just draw on the graph and figure it out. But it's actually the number of vertices minus 1. Okay, this one actually might involve Prim's algorithm in a moment. It says, first part, this is the easy part, give a mathematical term, describe a graph that represents the cables. So they want to know the shortest total length that'll be used to form a connected graph. That's slang for tree. So that is actually, now you've got to put all three words. Minimal, why? Because it said shortest total length. Spanning, why? Because it says it's going to be a connected graph where you connected all the rides up. And then tree, because that's what it is. Okay, now we have to actually show the minimal spanning tree, and that's Prim's algorithm. So let's have a go at that with the rules. And rule number 1, choose the edge with the lowest weight or value. And if we look, we'll see that that's actually the 50. All right, there's no other 50, so we don't have to worry about anything being the same. Now, rule number 2 says choose the next lowest weight edge that is connected to that edge. So connected to that edge, at this end, we've got these 4, and at the other end, we've got these 2. So all of those yellow ones are the ones we're considering, and you can see, obviously, the 100 is the lowest value. So if we just highlight the 100. All right, now, we then have to think about what's connected to that. Now, this one is already out of play because that'll break our rule about making cycles or loops. So we can actually say that this one is definitely out. All right. Now, what else do we have to look at? We have to look at still these, this, and this. They're all in play now. Now, what's our lowest value of that? It is, of course, the 100 again. So I'll just call it the 100. And you can see the process we're doing here. And so again, this one is out because that will create a cycle. Now, logically, if you're thinking about this, you've still got to connect the vertex up here. So you've got a choice between 300 and 350. Let's choose the 300. So that rules out the 350 again because it's going to make a cycle. Now, what are we considering? Well, this one's in play now, and this one, and this one, and this one, because all those yellow ones are connected to our red line. What's our lowest value? It's the 200. So let's connect the 200. And look, I don't have to go into a big depth explanation about this. Clearly, there's only one way to get to that one as well. And then we've got to consider the rest of the lines. Now, we've got to eliminate the 500 because that will make a cycle. And so what have we got left at the moment? We have got a 400, a 450, a 500 that is connected to the graph. The lowest value is 400. So we choose the 400. And then obviously to get to that last vertex, you're going to have to use that 200, and the 450 and the 500 are ruled out for making a cycle. Just to show you where that cycle is. So if you did choose the 500, this is all a face in here, isn't it? So we can't do any of that. And the same thing happens when you do the 450. If you do the 450, this is all face in there, and you're not allowed to do that. Okay, so there's our minimal spanning tree. It didn't actually ask us to work out the value, but they might ask you to do a value, and you just add up all the numbers in red. Okay, we've got a question that's asking about the minimum spanning tree, or minimal if you actually use adjectives, and we're told that we definitely must include k, so it includes the edge called k, which is this guy down here, and we know that means we're going to do Prim's algorithm. There's our Prim's algorithm. So if we've included k, we've got our highlighted yellow line. Looking along the whole thing, we've got this 5, a 3, and a 4. I'm going to include the 3. We've now got a 2, a 6, an 8, a 6 in play. Looks like the 2 is the best deal. That brings into play the 7 and the 7. So 4 is the best deal there. We actually have now crossed out a few, so we can't do the 6 because that'll make a face. Then you can see the next value is 2. Not hard to see that 1 is important. 6 is in play, so we need to connect that last vertex, which means we can rule out this dude and this one. And then over here, we've got 5, 6, and 8. We choose the 5. Now the 5 is in play. That's still the lowest one. Done, because these guys make a face. So we now have our equation, which is, and when you're doing this, make sure you circle things so you know which ones you've counted and which one you haven't, because otherwise you can get quite lost. Plus k, plus 4, plus 2, plus 1, plus 6, and we know that equals 33 because they told us that. You can get your calculator, but that's a 10, that's 20, 25, 27, 28. Why do people always have to add things in order? It makes it higher. 28 plus k equals 33. Therefore, the only thing that makes sense there is 5. 28 plus 5 does equal 33. There we go, all done.